name Hasib Shah. Today we will going to discuss primer designing for PCR and qPCR. So let's first understand that what is primer and how it works. Primer dictate the successfulness of a PCR. PCR is polymerase chain reaction. So primer is a template of the DNA, very short, about 20 to 22 nucleotides are in primer. So in what happened in PCR, first the 30 to 40 cycles of 3 steps. PCR consists of 30 to 40 cycles of 3 steps. In step 1 in PCR, denaturation occurs, and it is allowed for 1 minute at 94 degrees centigrade, which allows it to denature. So when denaturing happens, then we had already added in master mix primers, which are complementary to the DNA which we want to amplify. So what happened? The primer anneal with the complementary strand of DNA, which has been renatured in step 1, so it can easily anneal with the bond with the template strand. So now this is step 2, and it happens for 45 seconds. Time can vary with the requirement of PCR. Maybe I give time for 50 seconds, you may give it 40 seconds, so time can vary a little bit. And at 54 degrees centigrade, because temperature will be lower, so it can anneal, it can renature with the DNA. So this time primer will renature with the complementary strand of DNA. So in third step, what happens? We give the 2-minute time at 72 degrees centigrade, and so the only the RTPs will bind and that DNA tag polymerase and enzyme tag DNA polymerase will start building from the primer complete DNA strand, and the amplification of the DNA will happen, as you can see in this. Primer should be specific. Before you start designing primer, keep these questions in your mind. What are the primers for? General purpose amplification, real-time PCR, degenerate PCR, multiplex PCR. What do you have to begin with? So let me clear one thing. If you want to know what is real-time PCR, what is general purpose PCR, degenerate PCR, multiplex PCR, then ask me in comment. I will make videos for that also. What do you have? So moving on, what do you have to begin with? Single DNA protein sequence, multiple DNA protein sequences, sequence files, gen bank, ID gene symbol, RSNP ID. After you have your primer designed, consider a second opinion. Most likely your primers can be designed by several different softwares. Okay, so we can first artificially make some primers on internet, so then we can order our primers. Different software may vary significantly in concepts and overall approaches, designing criteria and default setting, comprehensiveness, usability, accessibility, and speed. Consider a second opinion when you are new to such design task application. You don't have a lot of confidence in the initial result. General rules for primer design: primer and applicator length. So these are some rules which should be followed. These are general rules apply to every primer which has to be made or designed. Primer length determines the specificity and significantly affects its annealing to the template. Too short, low specificity. It can bind to any sequence, because if there is a short length primer, there is a possibility that 456 nucleotide can easily be found in any DNA sequence anywhere. So not too much long, not too much short, because if it is primer is too short, it will cause non-specific amplification, and if primer is too long, it decreases the template binding efficiency at normal annealing temperature due to the higher probability of forming secondary structures such as hairpins. It means that primer can bind with its own ends and form a hairpins. So the optimal primer length is 18 to 24 base pair for general applications, 30 to 35 base pair for multiplex PCR. Optimal amplicon size. The amplicon is which is going to be amplified. 300 to 1000 base pair for general application. Avoid less than 3 kb. It is a limit for PCR. So if you want to amplify bigger DNA, then we can go for other like plasmid, virus, or different sources to make gene libraries. 50 to 150 base pair for real-time PCR. Avoid greater than 400 base pair. General rules for primer design. Melting temperature. The TM is a temperature at which 50% of the DNA duplex dissociates to become single-stranded. For denaturation, it is determined by primer length, base composition and concentration, also affected by the salt concentration of PCR reaction mix. Working approximation, TM can be calculated by this formula used to know it, that TM is equal to A plus T in bracket plus 4 G plus C in bracket, suitable only for 18 mer or shorter. If the primer is 18 mer or shorter. So these A, T, and G and C are the number of nucleotides of A, T, and G. The value will be taken from the primer, in which we will take how much A are present in our primer. So we will write the number here at A. The value of A will come from them, and as for T and G and C, B, G, C, and T numbers will be taken from the primer. So this must be understood. Optimal melting temperature is 52 degrees to 60 degrees centigrade. TM above 65 degrees centigrade should be generally avoided because of the potential for secondary annealing. Higher TM, 75 degrees centigrade or 80 degrees centigrade, is recommended for amplifying high GC content targets, because GC are very tightly bound. For denaturation of them, we need higher temperature. Primer pair TM mismatch. So significant primer pair TM mismatch can lead to poor amplification. Desirable TM difference is less than 5 degrees centigrade between the primer pair. The two primer pair temperature must not be different than 5 degrees centigrade. General rules for primer design: specificity and cross homology. So what is specificity and why is specificity determined primarily by primer length as well as sequence. Primer length, as we talked before, and sequence. The adequacy of primer's specificity is dependent on the nature of the template used in the PCR reaction. Cross homology. Cross homology may become a problem when PCR template is genomic DNA or consists of mixed gene fragments. Primer containing highly repetitive sequences are prone to generate non-specific amplicons when amplifying genomic DNA. Obvious, because it can bind to anywhere. Avoid non-specific amplification. Blasting PCR primers against NCBI non-redundant sequence database is a common way to avoid designing primer that may amplify non-targeted homologous region. So before going to do wet lab, we go for clinical lab, and we can do blast our primer sequence against databases. So it will show us that how much non-specific amplification can occur, which we can make changes to our primer and we can avoid. Primers spanning intron-exon boundaries to avoid non-specific amplification of DNA due to cDNA contamination. Primers spanning exon boundaries to avoid non-specific amplification of cDNA due to gDNA contamination. General rules for primer design: GC content, repeats and runs. Primer GC content, optimal GC content is 45 to 55%. Common GC content range is 40 to 60%. Repeats, consecutive dinucleotide. Repeats increase mispriming potential. Okay. The maximum acceptable number of repeat is 4 dinucleotide only. General rules for primer design: primer secondary structures. Hairpins formed via intramolecular interactions negatively affect primer template binding, leading to poor or no amplification. Acceptable delta G free energy required to break the structure: kcal per mole for 3 and hairpin greater than -3 kcal per mole for internal hairpin. Self-dimer, homodimer. Hairpin we had already talked about it before. So what is self-dimer? Two primer bind to each other, so it is called self-dimer. Formed by intermolecular interaction between the two same primers. Cross-dimer formed by intermolecular interaction between the sense and antisense primers. Okay. General rules for primer design: GC clamp and maximum max 3 and stability. GC clamp. What is GC clamp? Refers to the presence of G or C within the last 4 bases from the 3' end of the primer. Essential for preventing mispriming and enhances specific primer template binding. Avoid greater than 3G or C's near the 3' end. Max 3' end stability refers to the maximum delta G of the 5 bases from the 3' end of the primer, while higher 3' end stability improves priming efficiency. Too higher stability could negatively affect specificity because of 3' terminal partial hybridization induced non-specific extension. General rules for primer design: annealing temperature and other considerations. So annealing temperature versus melting temperature. Annealing temperature is determined by the Tm of the both primers and amplicons. Optimal Ta is equal to 0.3 multiplied by Tm. Primer plus 0.7 multiplied by Tm product minus 25. This is formula. We can have an optimal annealing temperature from that formula. General rule is Ta is 5% 5 degree lower than the TM. Simple as that. If you don't want to go for this a long formula, you can get your TA from directly minusing 5 from melting temperature. Higher TA enhances specific amplification but may lower yields, crucial in detecting polymorphism. Primer location on template dictated by the purpose of experiment. For detection purpose, section towards preprimer may be preferred. There are some sources on internet on which we can design our primer first to avoid any problem in future. Primer 3, Primer 3 Plus, PrimerZ, Primer RTPrimer Vector NTI Advantage 10. These are the sources, their names, Primer 3, and websites link are present below. General purpose primer design 2, Primer 3 Plus, general purpose primer design 2, PrimerZ, general purpose primer PCR primer design 2, PerlPrimer, Vector NTI Advanced 10. Primer design resources for real-time PCRs are these 6. You can pause it and watch their information about these online primer designing tools. So thank you all for today, and please subscribe and share my channel and like it. Thank you so much for your patience, and hope it will satisfy your hunger for knowledge. Thank you.